will share. Then you will have 15 minutes. If you have questions, type on the chat.
Okay, can you see my slides?
Yes, perfect. Thank you.
Thank you. So, hi everyone, my name is Daniel Cordeiro, and I will be presenting today how we are accelerating the smart city simulations tools of our InterSCity project. This is a joint work with Francisco Rocha e João Fukuda from EACH-USP and Dr. Emilio Franceschini from UFABC. So, the InterSCity simulator is an easy-to-use parallel simulator of traffic scenarios written in Erlang by InterSCity researchers. The use of such simulations is key to better understand more urban mobility. The simulator is able to simulate most city-scale scenarios, but some performance limitations restrain its use for large metropolitan areas. This work presents a two-level approach to accelerate the InterSimulator execution on larger scenarios. On a higher level, we accelerated simulation by learning and reusing recurring mobility patterns, while in a lower level, we show how we have used profiling techniques to identify bottlenecks and optimize process and memory consumptions. For the optimization of the simulation itself, we use an approach inspired by the SimPoint technique. It's a technique that was developed to accelerate hardware simulations. So computer architecture design simulates the execution of computer programs on new hardware and study them using metrics such as data cache misses, number of instructions per cycle, branch mispredictions, etc. So the idea of the SimPoint techniques is to speed up these architectural simulations by only running a small portion of a program and then extrapolating the complete behavior from this small portion. In order to find good representative small portions of the simulation, the computer program is first divided in what's called basic code blocks. It's sections of the program code that are executed from start to finish with one input and one output. And then, using these basic code blocks, the simulation is divided into intervals composed by several basic code blocks that behave similarly concerning the chosen performance metrics. The different intervals are compared using a structure called basic block vector, a vector of the size of the number of the blocks that a given interval contains, a metric to measure the distance between two basic block vectors, such as the Manhattan distance, for instance, and a clustering algorithm to find which intervals are similar. So in the example of this on this figure, we can see three intervals, the SimPoints, that were chosen to represent the three different behaviors detected on this particular code. The behaviors are represented here in red, blue, yellow. So you have three kinds of behaviors and three representative points that are the SimPoints. We are working on adapting the SimPoint method to use this on urban traffic simulations. So our method that we call simulation estimation by data patterns exploration analyzes the simulation event data produced by the InterCity simulator, identifies the recurring simulation patterns, clusters the similar behaviors found, selects a representative behavior from each cluster, and estimates the remaining simulation using the patterns learned. Our performance metrics in our case are related to the flow of the vehicles in each road in a city or town. So for instance, use the number of vehicles at a given time or the average speed of the vehicles on the road at a given time. So instead of looking at particular values of the performance metrics, we look at the simulations intervals as time series of the performance values. So in other words, our basic code block is defined as the time series that represents the flow of the vehicles on a road of the city at a given time. So we're looking at this time series of the vehicles on each road. In order to compare the time series and cluster the similar ones, use a method called K-shape instead of the K-means used by the original technique, because we are comparing time series. The centroid is chosen has the representative time series of each cluster. So the idea is to use the node performance of this representative to infer the performance of other time series in the same cluster without needing to simulate all the trips in those roads. But to infer the performance of each road, we must be able to map the centroids to each time series in the same cluster. So even if the centroid have the same behavior of other time series, even we can think about it as having the same overall shape, they are different. So we created a method that allows us to reshape the representative. So taking the representative, shifting it over time, compressing or stretching it, so it will look like each of the time series in the cluster. So we're trying to make the representative look like each other of the time series in the cluster. So for example, here in the figure, you could have the centroid depicted in red and one of the time series in the cluster in blue. Using a technique that's known in the literature has the dynamic time warping, we can estimate the blue time series using a minimal set of data about how blue diverged from the red on a previous simulation, and executing the simulation of the road represented by red in the new simulation. So use this, we take how blue diverged from red, re-execute red, and we infer that the blue will change its behavior, but in a similar manner how red changed. So we assume that in this new simulation, the blue will differ from red in the same manner. So in other words, the idea is that if a red changes its behavior from the previous simulation, the blue will also change its behavior on a similar manner. So we can estimate the new blue. Of course, this mapping technique is error-prone. It's an estimation, but our experiments have shown that the error in this estimation, in the estimation of the time series from its representative, is less than 6 times 10 to the power of -6, which we find to be very low. The figure here shows an original time series collected from the first simulation in the left in red, and our estimation for the same time series from a representative in green. So looking at in a visual manner, we can see that they are very similar. So our estimation is quite good. So I want to show a second experiment that we made where we have evaluated how well our technique can estimate the metrics of interest in reusing results from previous simulations. So in this experiment, we have a new scenario with 11% more traffic lights, with 11 more traffic lights being simulated, but the simulation is reusing data from a previous execution of the simulation without these extra traffic lights. And the metrics of interest are shown here in the figures, the metrics that we computed using our method. So average speed and occupancy rate is compared to the result obtained from the original InterSCity simulation. We found that our method estimated the average speed of the new scenario with a maximum error of 2.5% and the street occupancy rate with an error lower than 35%. An important point to consider is whether it's better to apply our technique or run the entire simulation, since you are doing some estimations that can decrease a little bit the accuracy of the simulation. So our technique has 3 stages. First, a preprocessing stage in order to detect the recurring behaviors, and we execute we cluster similar roads and pre-compute how to reshape the centroid to each of the time series in the same cluster, what we call warping path. And this learning phase is done using results from previous simulation. So at the right, we have the time that we spent for this scenario to do this pre-processing phase. Then the second stage can execute the simulation, reuse the behavior learned. The user can choose how much of the learned behavior can be reused. More reuse of these behaviors, the behaviors from previous results, results in smaller execution times, but potentially bigger errors. The figure on the left shows in blue the execution time of the execution of the simulation using our method for different percentages of reuse of the learned behavior. So the more we reuse the learned behavior in the left, the smaller execution times. The less we reuse, the more we re-execute the simulation, so bigger execution times. The yellow line on the top shows the amount of time needed to execute the entire simulation from scratch. We also conduct a series of low-level performance profiling and optimizations of the code of the InterSCity simulator. So in order to investigate processing memory bottlenecks, we applied virtual machine level and application level profiling techniques. So in the virtual machine level, we are looking at what happens inside the Erlang's virtual machine, and using application level profiling, we are looking at what happens inside the simulation code itself. And for that, we use the Linux Perf tool. Our application level profiling detects performance degradation on functions relying on multi-process synchronizations that uses Erlang's ETS data structure. So the ETS is employed by the simulation code to track the status of all roads. Information about maximum speed, number of lanes of each road, the current capacity of the road are accessed by multiple threads during the entire simulation. So the simulation needs thread safety, but the data structure implemented by these ETS tables is much more sophisticated than we actually need. So based on our findings, we have investigated three different approaches for low-level optimizations. The first is implementing a custom storage library made in using Erlang's native implementation functions, NIFs, to implement a lightweight data structure tailored to our list streets table needs. The list streets is this table that contains information about simulation for each one of the roads. The second low-level optimization was trying to use internal functions of the Erlang runtime system in order to use the Erlang's virtual machine facilities to make more faster insertions, lookups, and updates in these tables. And the third optimization was porting the simulation to use the newer version of the Erlang OTP platform, which introduces a new just-in-time compiler. Our experiments show that our lightweight data structure made the InterSCity simulator run 28% faster. Using built-in functions resulted in good performance on big benchmarks, but these results are not so good for accelerating the entire simulation. So it was good in micro benchmarks, but does not help it that so much, or does not help it like our implementation using native implemented functions. Our performance evaluation also showed that the use of this new just-in-time compiler introduced in version 24 of the Erlang's OTP was able to execute the simulation of larger scenarios up to 4.5 times faster. So this effort in rewriting the implementation of the simulator using this new version of Erlang was worthwhile. In conclusion, we are showing here a two-level approach to improve the performance of the InterSCity simulation. Our method was based on the SimPoint technique, is able to reuse knowledge acquired from previous results, and our preliminary results show that we can estimate behavior of roads with very little error, and even that we can extrapolate old simulation of the results to new scenarios with limited errors. Our high-level method allows the user to choose between speed and accuracy. If errors can be tolerated, the user can choose to reuse more information from previous simulations in order to have a faster result. So this is something interesting and that we want to study further. we also showed that significant performance improvements can be obtained with low-level optimizations. And for future works, we are currently working on evaluating the performance using real-world mobility patterns. So you saw that we have these small experimentations trying to understand if our hypothesis that we can use the scene points to accelerate the simulation is a good hypothesis. So we are investigating more that, but we didn't have yet more experimentation using real-world mobility patterns. So I try to gather more data to make larger simulations. And another idea for future works to parallelize the preprocessing stage. So you saw that the preprocessing stage takes 1/6 of the total execution. Of course, the preprocessing we can make, or we can execute only once, but it would be interesting to try to parallelize this and see if we can do it faster. So this is it. Thank you for your attention, and I'm open to questions.
Okay, thank you, Daniel. So a problem with the InterSimulator right now is that, for example, to simulate the Great São Paulo, which has 40 million trips per day, it takes around 10 hours on a very big machine with lots of cores and lots of memory, which makes it difficult to do an interactive analysis trying different possibilities, for example. So do you believe you will be able to run such a large scenario in in my notebook that only have 16 gigabytes of memory and not 100, and like in 1 hour or less? And if you do, when do you believe you reach that result?
Tough question. I don't know yet, because we didn't study yet the use of memory that our method requires, but we are already able to execute it faster. So only using these low level performance optimizations that we did, we can run this up to 28% faster. So this is good news already. The other thing is that using this higher level optimization, using the scene points, we can try to make simulations faster, introducing a margin of error. So I can say, I already executed the simulation using 10 hours, like you said, and I want to test a scenario a little bit different. That's almost equal to the previous scenario, but it has, for instance, more traffic lights or a new road or something. And we can do this by learning the behavior from the previous simulation and reapplying this behavior to the new one. And this can be very, very fast. But we don't know yet the margin of errors for larger simulations. And this is something that we are working right now.
Okay, thanks. Nelson Lago has a question. Would it be possible to eliminate the pre-processing step and instead do it on demand together with the rest of the simulation?
No, the pre-processing step is important for us. So the pre-processing step is one simulation. So we can execute the one simulation, analyze the data generated by one simulation to try to execute newer simulations, new scenarios, or different simulations using the data from the previous one. So we need to learn the behavior from the previous one. So we need the pre-processing. We can try to do this on demand, but I don't know if it's better. Probably not.
Okay. Yeah, Nelson. Apologize for understanding it incorrectly, but asking you
No
should
problem.
never apologize.
I apologize, baby. The presentation
you
was not
should
that
never
clear.
Apologize for asking a question. Yeah. Okay. So I guess we are done for today. today. Thank you very much, Ed, Alessandro, and Daniel, for the nice presentations.